Someone, a couple of pupils once said to me, thank God this one is recorded, because this one is one of the more interesting ones, but it's tricky. So, what are we going to try to do? We are here, right? So I've just made visible threads, mutex in C, so that's like an example. We'll go through some more examples here, and race conditions, okay, and critical sections. So we won't get through all this most likely today, because if we do it, probably your head would spin off. So we'll go through as much of it as seems sensible, and then we'll finish off the rest of it in the first portion of our labs next week, and then we'll start into the actual labs relevant to this area. Okay. So essentially what we're going to do is we're going to talk about threads. We've done a lot of talk about processes and resources and all that sort of jazz. Now we're going to talk about threads and what that leads on to, the advantages of them, the disadvantages they cause, and how do you resolve it, okay? Because there's lots of benefits of threads, but there's issues as well. So let's go on and have a chat about threads, right? So we're going to talk about these ones. We're talking about, typically this is how they're represented. In other words, you've got one process, and inside a process you have decided to create multiple threads of what's called execution in that process, all right? So you'll understand it more in a few minutes, hopefully. So what are we going to talk about? We're going to talk about our states again, like our ready and our running and wait and all that sort of jazz. Concurrency. Does anybody know what concurrency means? Does anybody know what concurrency means? Hard to answer a question. It's 3 minutes past 9. Do we know what concurrency means? We're looking it up. It means doing things at the same time, okay, in parallel. Yeah, well done, Kelvin. I'm going to talk about performance, obviously, that's what all this is about. A lot of comparison between processes and threads. How would you actually implement a thread? Two different types. These are them user level threads and kernel level threads, and advantages and disadvantages. All right, so that's what we're going to be talking about. And I'd say what I will do is I'll, if you want to get your Linux environment ready, I will flick through an example on it, because I find what it does is if you do the example early in the process, it helps people understand what the hell this is all about. Okay, so you may get your system set up as well in parallel if you want to play it off. All right, so at a very, very high level view, right, we have this sort of diagram here. And this is where we've been operating at the moment, right? Which is one process, one thread. And very simply, if you go over here and you type, or I type in this case. Okay, so if I type ls, I've nothing else, so it's probably not the best example. Let's go back up one. Okay, so I typed ls minus lrt there, right? So ls, if you remember, is a program. Where is it? It exists in a place called /bin, right? There's all our executables that Linux gives us, all our command line stuff, copy, cp, mv for move, and ls is there somewhere. There it is there, okay? That's a program. When we called it like that, we created a process, one single process with one single thread of execution, all right? And all it did was it listed the stuff in the directory. That was it. Very, very simple process, one thread of execution. Okay, that was, we've been used to that at the moment. Nice simple thing. If you wanted to actually do two things in parallel, we know that we can, we can go over here and we can, we can type ls minus L, and we can put it in the background, right? And while it was doing it, we could type another one, yeah? So we could do something that was long. So I can go sleep 20, right? That's in the background, and I can go ls minus lrt, and I've run two processes in the background. So I've run two processes. One's in the background, one's in the front, but there's actually two processes running there, right? They both have a single thread of execution. They might be wanting, I might have those that they actually talk to each other as well. But the point is, I could have a design of stuff that had multiple scripts. I could run them in parallel and they will happily run away, and they're what's called single threaded. All right, nothing sexy about those. Now, if we go over here to this side of the diagram, especially in programming land, not so much in scripting land, but in programming land, what we can do is we can decide that actually, yeah, do you know what? My process, I want to split this into multiple threads of execution. Now, why you would do that, we'll talk about in a minute. But I have the ability to do that. So I have one process that starts off, it has one thread of execution, but then I decide actually fire off another threads, a few threads of execution in this process. Maybe there's things I can do in parallel. And while I'm waiting for I/O, while I'm waiting for someone to be doing keyboard entry, instead of my process being stuck waiting, well, why don't I fire off another thread of execution, because I know I have to do some number crunching, right? So you can do that. You can have a process with multiple threads in it, right? And I'll show you that later on. And then the ultimate is, this is modern programming, whether you like it or not, you have multiple processes with multiple threads per process, right? It's quite complicated, which means you have more bugs, blah, blah, blah. But what you're trying to do there, why do you think we've got to this state rather than why didn't we just stay here? Why did we end up with more complicated designs like this? Why would you do this on a modern computer? Why would you do that? I'm sure there was lots of complicated things to do 30 years ago as well, but why would you do it? Why would you do your design like that? Because it's going to be more complicated, it's going to be more bugs in it. Why would you do it? Speed, but what? Why do you get more speed? But why? What are you trying to take advantage of? I'm looking for a certain thing here. You're getting closer. What's the difference in modern computers to 15 years ago? Yeah, exactly, Luke. Well done. There's more cores, all right? So if I've got more cores in my phone or whatever, I can have multiple threads of execution running, one on each one of those cores, so I can get more things done in parallel, all right? And that's the fundamental difference. Like 10 years ago, phones were single core, then became dual core, then became quad core, now they're octo core, all right? That's just the way computing has gone. And so in order to take full advantage of that, you can thread your designs so that you can be run on separate cores. You can have separate processes on separate cores as well, but threads are nicer, they're a lot more lightweight, as we'll find out. Okay, and a lot of the times they make sense to use. So let's keep going. So that's the very high level idea. With a theory waffle, instruction streams, hardware can interpret n instruction streams at once, right? So if it's a single processor, there's just one. If it's dual, there's two. There's octo, there's 8, right? And the whole point is concurrency. We want to get more things running in parallel, which means we can increase throughput through the system. And if we have multiple cores, we want to take advantage. The last thing you want to do is if you have a quad core system and all your software is just designed to run on one core, that would be pretty crap, all right? So let's just have a think back to our process states. Remember, we had 3 main ones, right? We won't get into suspension and resumption here, right? So we had ready, running, and waiting. We'll all remember that, right? So a process will only perform computations, right? Fancy word for it, use the CPU, when it's running on the process. So fair enough, right? If you're in ready, if your process is in ready or in waiting, you're not actually using the CPU. Some other joker is using it, okay? And it might be your quantum. So if you're just flicking between ready and running, remember you're just probably number crunching, your quantum is up and you're hoofed back here, someone else goes in for a quantum, right? If you're in waiting, it means that you're waiting for something to happen. It might be keyboard entry. It could be that you're talking to, you're writing out to a file. Why would you be, actually, here's a question for you. If I've got a process and it's doing some number crunching and then it has to write out to a hard disk or an SSD, why does my process go into the waiting state while it's writing to that SSD or hard disk? Why does it go into that state? I'm not waiting for any keyboard entry or anything like that. Why does it do that? Why doesn't it just stay in the running state? Any ideas? I know it's early. Any guesses? I won't bite. To allow for 4. Yeah, obviously, but why? Why doesn't it? Why? Like, I've been bombing along here doing some number crunching. Then I want to write the result out. Waiting for resource. What resource are we talking about, Calvin? I have, say, access to the result. I have access to the file. I have the file open. I can write to the file. Why, when I'm writing to the file, do I end up going into the waiting state? I'm just writing to a file. I'm not waiting for someone to do me input or anything. Why does my process get hooked onto the waiting state? No, there's no user input here. What am I waiting for? It's a hard question. Let's put it on the CA or an exam or something. What am I waiting for? What I'm waiting for is actually the hard disk or the SSD because it's slower than my processor, right? My processor is bombing along and the DRAM is bombing along. They're all flying along at top speed, right? Yeah, exactly, Andre. If I'm writing to a file, typically that peripheral, that file, which is on a hard disk or an SSD, is a slower piece of hardware, right? So if I were to stay in the running state while I wait for that to write so I can move on, I've deprived that CPU from someone else, right? So when you write to a slower peripheral, as I say, like an SSD or a hard disk, you will end up going into the waiting state while you wait for that peripheral to say that's done so you can move on, okay? So your process will go into the waiting state. And then when that confirmation comes back, you'll go back to the ready and then you'll be scheduled again, all right? So that's why when you're doing I/O or when you're doing user input like keyboard or whatever, you will go into running, then waiting, then ready. All right. It's very, very important that you understand that when you're talking to slower peripherals than your DRAM and your CPU, right? Okay. So with that in mind, we want to stay in the running state for as long as possible. So I see here, I/O advanced writing to disk can reduce the time processing the running state, increasing the amount of time it takes. So what we want to do is we want to improve that situation, right? Because we can, so think about it, right? If I single thread, my screen there. Sorry, my screen just timed out. Okay, if I single thread my program and I'm writing to a disk, my program will go do something right, and it'll just all be sequential. Okay, so if you think about it, if I multi-threaded my program, and while I was writing out to this I/O or disk, right, I also had a thread that could continue my computations, I would be using the CPU all the time. Can you see that? Hopefully you can see that, right? So there is an advantage of multi-threading my program, if it suits, to take more advantage of the CPU. Because otherwise some other process is going to get the CPU, right? Because the scheduler is not just going to sit there, give you the CPU and wait for you to finish talking to your slow peripheral. It's going to go, oh, someone else can have it. And then when his peripheral comes back to say it's written, I'll give it to you. Okay? So I've talked a lot there, and this is what these words are. We would like to maximize the amount of time a process can remain in the running state so it'll finish more quickly. And we know there's two things we like to do: computation, right, which is number crunching, crypto, whatever you want, and I/O interaction, right, which is waiting for users, writing to files. Computations can be performed while we're waiting for the I/O because the process, if process is in the state waiting, then some other process is going to be allowed to run. So if we multi-thread it and one of our threads is in waiting, another one of our threads could be running. Okay, so that's all that's basically trying to say. So it means, there we go, if we can do the two of them at the same time, the process is running to, we need to divide it into threads. So threads are like sub-processes. One of them might read data from a user or write to an I/O file. And the second one, in this case, might be just incrementing counters performing large computations. So this one, too, can continue all the time while we wait for the user. So just to finally say it one more time, if we thread it, sub-process run 1, when it's reading data from the user, will be in what state? What state will that sub-process or thread be in? Anyone? When you're waiting for data from a user, what state are you in? Are you in ready? Are you in running? What state are you in? You're waiting. Whereas this one can continue to be in running. Okay? So I've multi-threaded my process. I can now do the two things at the same time. If I don't thread it, while I'm waiting for stuff from the user, my process, which only has one state, will be in waiting, so I can't do this. Whereas if I multi-thread it, I can. Okay? That's what's important. So, so far, we get a little bit, gets a little bit tricky here. We've seen concept of a process embodies two concepts, right? Scheduling and execution, I think we all can get that, and resource ownership, right? We've talked about deadlock and everything out the yazoo at this stage, right? So I think you all understand the importance of owning resources and all that sort of jazz. Could be files, could be printers, could be anything, right? And scheduling execution, that's really, really important because we're trying to maximize the CPU time, okay? We should try and consider them to be independent of each other, right? And new operating systems do that, and there's good reasons for that, and it's all to do with this thread stuff, all right? So hopefully by the time you finish it, you'll get it. If not, watch the video back again and try to get it, all right? So we're going to look separately at these two things, execution control versus resource control, all right? So execution would be how we use the CPU. Resource would be how we control our resources, our files, our variables, things like that, access to them. So let's have a read of this. There's a fair bit in this page. In a modern system, a unit of dispatching is essentially called a thread. Another word for it is a lightweight process. Makes sense, right? It's like a skinny process, right? LWP is actually what's called a kernel level thread. We'll talk later exactly about what is a kernel level thread, right? So that's a unit of dispatching. Essentially, it's a thread. A lightweight process. A unit of resource ownership is still a process, right? And there's going to be a reason for that. And I'll tell you in advance what it is, right? To make it easier for you. And the process, if you have a process with multiple threads, the process is the person who's responsible for handling the resources, right? Whether it's files or access to files or access to variables and counters, right? Whereas the thread is purely responsible for the multiple execution threads, right? It has to share, it has to use the process idea to share access to files or whatever, okay? So you'll see it when you see the diagram come up. This is a nice diagram come up. There's the diagram there. We'll talk about that in a minute. The traditional single-threaded approach contained a single thread or execution trace per process, right? So remember this little diagram here? Yeah, single thread per process, whereas this is the more complicated one. Back here. Multi-threading refers to the ability of an OS to support multiple threads of execution within a single process. That's what multi-threading is all about. All right. So let's have a look at the diagram, and it might make it a little bit clearer. Why not? This is a very, very important diagram. All right. If you're ever asked a question in an exam or whatever, see about processes versus threads, this is probably the single most important diagram if you can explain this diagram. So on the left, we have a single process, okay, like ls or whatever. And what we see is there's one thread of execution, which is fair enough. ls literally starts off and it goes blah, 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 list all the things that are on the screen. And up here, as part of this as well, we have the code for ls. Well, we know somebody has created the code for ls. It's stored in that /bin directory. When ls runs, it might have some variables, all right? It might have some counters or whatever variables that it keeps. And it might have some file handles, right? So I did ls, but I could have done touch. I could have done copy, F to FF, or just files, right? Yeah. In that case, so let's take the copy one, right? If I did the copy, there's two files, the source file and the destination file. So what would actually happen is the two handles for those files will be stored in this area. Okay, so any thread of execution who wanted to be able to play with those files, open those files, read those files, write those files, would use the handles that are stored here. Okay. Also, what we have, and see there's a line here. All right. So okay, there's some difference between here and here. So a typical process as I said, it has the code. When you run the code, you step through it, right? Remember your computer architecture from first year? Do you remember and you had all your machine code and you had your load this and move this and branch to here. That's essentially the code, right? Every piece of software that runs boils down to those assembler little commands, right? That's the code. So this line here separates these two though. So registers and stack. So again, if you remember your computer architecture from first year, you did it with probably, who did you do it with? Martin and Mary, was it? Or was it just, no, it was probably just, who was it? Margaret. Is it Margaret still teaching you computer automation? Maybe. Margaret. We do it. Okay, so there's a few people. Okay, sorry, fair enough. Anyway, you will recall when you were doing it, you know, you remember you're stepping through all that code and you could see the registers. Remember there was A, B, C, and D and all that sort of jazz. And there was the stack and you could push and pop things onto the stack. Remember that? So those two things there are regarded as being execution relevant. And that makes sense. In the registers, you've got things like the program counter, stack pointer. Remember all those things? So you will always have those for a thread of execution. But why is this line here? Well, this line is here because when you move over to the model of a multi-threaded process, you still have one copy of the code, one copy of the data, one copy of the file handles. But for each thread of execution, you have a copy of registers and stack. See that? And there's a very good reason for that. If you have a separate thread of execution, you need to have a separate set of registers and stack. Now, is there any brain box in the room can tell me why you would have to have a separate set of registers? And I'll give you a clue. It's to do with scheduling. Anybody? That's a tough question, by the way. So, if you think about it, remember we did scheduling and we did context switch. Yeah, very good, Kelvin. That's pretty good. So remember we did a context switch, and what happened when you did a context switch? So remember, a process is on the CPU, it's running away merrily, right? And then its quantum uses up. So in this case, it's a thread that's running, right? Its quantum is used up. What happens? It gets hoofed off the CPU. So remember what happens. A copy of the registers of the CPU gets stored into the control block. Do you remember that? So this is essentially the control block for a thread. And the reason for that is when you then put it back on the CPU, when you get another go, it needs to continue from where it started, from where it stopped. So the copy of the registers gets put back into the registers on the CPU, and the CPU lets you run again. Okay? So each one obviously has to have its own, essentially, control block stuff where the registers are stored. So I won't call it a process control block in this case because it's a thread control block. All right? But you should get the idea if you understood the context switch from a few weeks ago. So each one of those needs that, but it doesn't, see this here? It doesn't get its own copy of these. And this is the really important thing when we said that the unit of resource ownership is referred to as the process and dispatching is the thread. The process is in charge of these three. All right? So this is a process, it's multi-threaded. So you have stuff that's relevant to the threads and you stuff that's relevant to the process. And the most important thing you need to realize is that is shared. Therefore, when you access it, you need to be very careful. Say that was a counter and these were writing to that counter. If you're not very careful, remember how we saw when I showed you the lock test with the script I was writing to the screen. The screen is essentially a file handle, right? And if you weren't careful, you got a corrupted output. Oh, remember, we put it into the file and we got a corrupted output. Well, imagine if this was in a program, right? A Python program, or Java, or a C program, and you were writing to the file. You've got the exact same issue because there's only one person who owns the file. That file handle is shared between these. Okay, so hopefully you get that. So the code, global data, variables are shared, file handles are shared between these stacks, between these threads. But the threads themselves have enough in their space to be able to control their execution. Okay, so hopefully you get that. We'll keep going. So, thread implementation. In a single threaded process model, blah, blah, the representative process includes PCB, user, and user and kernel stacks, right? So that's basically just what that's saying, okay? And also, I think there's another diagram here. Yeah, okay. This diagram isn't as nice, I don't think, but it's not a bad diagram, okay? So we did PCBs, So a single threaded process model, you have process control block. The user address space is just the entire space that the process takes up in memory, right? And in there, you've got two different stacks. Don't worry about it, right? Basically, all this is trying to convey is that's a single process model. And when you go to a multi-threaded process model, what happens is everything to do with execution, you get a separate copy of it. But this, there's still only one of these. That's the only message there you need to watch. So anything to do with execution, you get a separate copy of it. Anything to do with resource ownership or the process stays the same. Okay? That's what those words are still trying to say. And this is really, really important. Threads share the state and the resources of that process. They reside in the same address space and have access to the same data. So if one thread opens a file for reading, other threads in that process can also access that file. And when we finish this deck, I'll show you a little example of a multi-threaded process accessing some variables, some data, all right? Global data, and you'll understand it a bit better then, okay? So let's keep going. So a closer look. Abstract entity, I don't know who makes up these words, probably me, that executes a sequence of has its own set of CPU registers, its own stack, and it has no thread-specific heap or data segment. Don't worry about that line for the moment, I'll come back to that line. These two lines are the important part, and these are the ones I explained when I explained that when you're getting context switched on and off the CPU, you obviously need your own register copy and stack, because otherwise, remember what happens when you get a context switch. You get stopped. So where you are right now, all your registers, all your program counters, all that sort of jazz, a copy must be made, right? It's copied in here, and then you're told to go away, and then another thread or whatever gets executed, and when he's finished, you might get another go. And when it's your go, these are copied back on to the CPU registers, and off you go. You run then for another 10 milliseconds or whatever. So hopefully you understand that. They're lightweight. Creating a thread is more efficient because essentially there's less to them, okay? The process has more stuff it needs to worry about. It has that code, it has that data, it has those file handles, right? The threads are lightweight. They're just purely about execution. Communication between threads is easier than between processes. Yeah, because if I go here, if I have a thread here and I want to talk to this thread, basically typically how it's done is just using maybe a buffer, or if I want to share data across to here, it's very simple. Whereas if I have a process and I want to talk to another process, I have to involve the operating system to send messages to and from between processes. It's a much bigger deal. It takes longer in comparison to just sending data from here to here. All right, they're quicker and they're more lightweight. That's it. Context switching between threads requires fewer CPU cycles. Yeah, obviously, because it's saving more, right? If you go back to what's stored for a process and put into the process control block versus just, saving off some registers, then it's quicker. They track a smaller amount of stuff, that's all. Okay, so they're more lightweight, therefore they're quicker, they're more efficient, okay? Some examples. Has anybody, there is some programmers in the room, has anybody used threads, POSIX threads or Windows threads at this stage? Anybody done anything with them? Yes, no, not yet. Okay. All right. So the important thing, you don't need to get upset if you haven't, right? Very few people have. The important thing what you learn is they exist, and did it too, Jared? Very good. Well done. Did it crash much when you were doing it? Yeah, exactly. Did you have any issues with it, Andre? Ah, okay, good man. So the important thing is they exist. The important thing is that they are modern computing, all right? And the most important thing is you understand what the hazards are if you treat them, and you have bad design. Okay, and that's what we'll do over the next few weeks. All right, so let's just have a look at a very, very simple example. This is just pure computing example here, right? In other words, computation. There's no file access, disk access, or user stuff here. All right, so very, very, don't worry about the fact that it's a for loop and see, it doesn't matter, right? Even you can understand that this is basically saying it's a loop from 0 up to a number. We'll say that's 50. It's basically just going to go and add up a load of numbers and store the total here. So what it's going to do, I say, tell a lie, going to multiply those two, going to multiply those two, going to add them together, and the answer is going to go there, right? And if that's done in a single process, single thread, it'll start, blah, 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 it'll finish, end up. Now, if we can split that into 2 threads, could we change the design so that we actually got the answer quicker? And the answer is yes, okay, because it's purely just number crunching. So if we changed it so that we did a thread from 0 up to say 50 and from 50 to 51 to or 49 or whatever up as far as 100 and asked the 2 threads to run in parallel, then it would happen quicker. It would only happen quicker on a multiprocessor core, not a uni one, because a uni one obviously there's not going to be any advantage. But on a multiple processor, this would now run in half the time. Okay, so hopefully you can see. Don't get bogged down about it. Most important thing is you understand if it's computational only, I can take advantage of this. Well, I can take advantage of it anyway. But here's a more interesting example. If we consider a web server and we have a single core, right? Can we be clever about our design so that we can we do things quicker? So if we consider a web server, right? Its fundamental thing, what it does is a message comes in from a remote browser asking for something. You might have to go and get that something from a disk, and you might have and you send a response out. So there's three things it does. Okay, so if that were single threaded, yeah, and we did it one after the other, and then other requests came in, it would just be able to do it one after the other. Very boring, right? But see that one there? That's the slow one, isn't it? So we could be clever if we threaded it and while into multiple threads, right? And while we were doing that, we might be able to handle other network messages coming in and other data. So if we think about it, there's that comes in. We go to get the disk. While we're doing that, that's slow. We could do this. And while we're getting that one, we could do this, right? And the gas thing is, the total time, but the most important thing is we could do that would work quicker on a single core, okay, if we designed it like that. So that's just why threads can even work on single cores if you design them properly. So this is an important one. I'm not going to read all that, right, because I think I've just waffled about the whole thing anyway, right? I'm trying to see if there's anything. Oh, okay, there is stuff in there. All right, so we'll read it quickly. A thread has no data segment or heap, right? So essentially, remember this diagram. There's your thread, there's the data, okay? And the heap, which we'll talk about. I don't think I will talk about heap anyway. Oh, I think I do, yeah, briefly. Anyway, it doesn't have its own copy of these. It just has what it needs for execution. That's what the message is. Yeah. Okay, whereas a process has blah blah. Thread cannot live on its own, it must live within a process. There's no such thing as a thread on its own, it has to be created by a mother. Okay, there must be at least one thread per process. So when a process kicks off, it creates essentially one thread of execution. There can be more than one thread in a process. The first thread's called main and a process stack, blah blah, doesn't matter. Threads within a process share, okay, fair enough, we talked about that. If a thread dies, its stack is reclaimed. If a process dies, its resources are, and all the threads die. So that's important. If you have a process with 15 threads and one of them dies, just the memory associated with the execution of that thread dies. If you have a process with 15 threads and the process dies, then the whole lot dies. Okay? So that's important. Inter-thread communication via memory, very quick. Inter-process come via OS and data copying. I say that takes longer. All right. So if you know you have a design and the little threads need to talk to each other, or whatever way you design it, the threads of execution need to talk to each other, and it's simple communications, then you might be better off thread it rather than use multiple processes. Okay. that's more complicated. Each thread can run on a different process, so can a process. So that's quite similar. Inexpensive creation and context switch, expensive. Relative, when we say expensive and inexpensive, just relative to each other. Okay, we're talking nanoseconds, but still, it all adds up. Advantages. It takes far less time to create a new thread. Again, in relation to how long it takes to take a process. We all know how quick it is, but threads are quicker. It takes less time to terminate it, fine. They can communicate, we've done that. A program continues to run even if part of it is blocked. Okay, so that's essentially, we're saying if you threaded it and if one part of it is waiting for I/O, then essentially you might still be able to continue if your other thread can do stuff. Whereas if you don't, it's just going to sit there while it's in the waiting state, okay? And multiprocessors can be used more efficiently, fine. Disadvantages, okay. This one is important, all right? What we will come on to in a little while is a thing called user level threads and kernel level threads, okay? Kernel level threads are essentially the way to go. And user level threads do have a place in life, but they have one big disadvantage, all right? And they're to do with, you can end up that the whole process is blocked. All the threads are blocked if one of them is waiting for something, all right? So we'll just read this. You mightn't fully get it until we do user level threads, but we'll try to explain it. Major disadvantage is that if a kernel is single threaded, no modern kernel is single threaded, right? Okay, so this was a major disadvantage years and years ago. But if it was single threaded, the system call of one thread would block the whole process, right? And the CPU would idle, whoopie-doo. Modern kernels are multi-threaded, but this block whole process does apply to ULT. Just keep that in your mind for a minute and I will come back to it, okay? And then you will understand it. And just leave that one for a minute in your brain. Security. Essentially, this is a security issue, right? Because if you look at this diagram, these are all operating in what's called the same process space, okay? So while this guy is executing, if he had a bug that had a pointer to a memory over here and he wrote to it, he will corrupt this one, okay? So if you get them wrong, they'll crash, all right? If you have a process and another process, the operating system guarantees that this process can never write to another process area. But if it's threads, they can. So there is a security issue. Similarly, if you've got somebody managed to infiltrate or hack into one of the threads, they are in the same space as these other threads, all right? So you have to be careful. And I've seen them crash if you get it wrong. Depends what language you're writing it in, okay? If you're writing it in C, which none of you will be, I doubt, then it's extremely dangerous. If you're writing it in a high-level language like Python or Java, then not so dangerous. But this is an OS course, so I need to talk about C. All right. So, thread implementation. In a single threaded representation, okay, fine. Single PCB, also separate text, fine. We've done that. That's the diagram. Threads share the same state and resources. Okay, that's the top line. They reside in the same address space and have access to the same data. Top line. And if one thread opens a file for reading other threads, okay, so we know that. Okay, that's that diagram. So again, don't get hung up on all of this. All I want you to understand is what's going to happen when we start talking about the threads, right? This is what's called a process address space, what we do. There's the code, okay? So that's like if the code for LS or the code for CP, right, is residing there and all the little load this and move this, they're all there. And as the program is running, the process is running, the program counter is pointing to a place in here where, do you remember the program counter from first year? And it points to the next instruction. Well, it's going to be pointing to somewhere in there. That's my global data probably, right? These are just libraries I might need, other code I might need, blah, don't worry about that. What's a heap? Maybe you know what a heap is? Maybe you ever heard of a heap? No, I doubt you have. But what's a heap? A heap is a lump of memory, a big buffer of memory that the OS gives you if you need to be able to create large arrays or buffers, right? It's an unorganized stack. Sounds like something from the web, but anyway. So you have two sources. When you have variables or arrays in a program, you have there's two places they come from, right? When you say, okay, give me an array of 100 bytes or whatever, there's two places that the OS can deliver that from. One is the stack, and the other is what's called a heap. And typically, large arrays or large buffers come off the heap, all right? It's just a block of memory that the operating system gives you and says, that's yours, you can use that while you're running. Okay, that's all it means. But it's controlled by the process, all right? So there's only one heap per process. If you've got a process with 15 threads, you don't get 15 heaps. You get one heap, you get 15 stacks, all right? So let's have a look. If we have a process with one thread, this is what we sort of end up with, right? So an LS would look like this, yeah? So it's running. There's a program counter pointing somewhere in the code where LS is running. So in other words, LS runs start to finish. At some stage it's, whatever, maybe it's about to do the output to the screen. That's where it's pointed in the code, right? There's a stack pointer. We have a stack for this thread. And remember, we have its registers and we have a state. Fair enough? So that's a single threaded process. If we have two threads, none of this other stuff changes, right? We still have one copy of the code. We still have one copy of the data. We still have one of these, but we now have a totally separate thread, okay? And we have a program counter that now points to a different place in the code because, remember, our two threads can be operating at a different place in the code because we've threaded it, right? That's the whole point. We want two threads of execution. Does everybody understand that? It's an important diagram from that point of view. Okay, and that's just basically what that's saying there. So it's important that you understand what's per process, which is these three and these two. And then every time you have a thread, you get an extra stack. And most importantly, in this TCB, which is a thread control block, you have a program counter, which points to where are you, this thread, in the code. Does everybody see that? Hopefully you do. Okay, now, I promised you we would talk about user level threads versus kernel level threads. So when you do P, for instance, if you use P threads, so Andre, I think that he said he did P threads or something, didn't he? Yeah, he did, yeah. He did a 2-thread app, okay? So Andre most likely was using kernel levels. I was nearly guaranteed he was using kernel level threads. All right? So let's consider kernel level threads for 1 second. Here we have our threads running, little squiggly tadpoles. We have user space, which is Andre's space, right? He's not, Andre wasn't writing the OS. He wasn't writing the kernel. He was taking advantage of some library that was given to him, pthreads or whatever, don't know what it was. And the kernel controls how those threads run, all right? So we have a process and we have 3 threads, okay? And the most important point is the kernel or the OS controls them. So they all have, for instance, their own state and everything like that. The kernel knows about each thread and it schedules each thread. Whereas, and this is the normal operation, over here you have another option for threads. It's called user level threads. And the most important thing is, you see here, the kernel knows nothing about the threads. The OS knows nothing about the threads. The thread implementation is controlled by some library of code that's written in user space. So this is like if Andre wrote his own thread handler. Kernel wouldn't know anything about it. It's up in Andre's space, okay? And he can have as many threads as he wants in there. And he can, his thread library, he can decide how he schedules them, how much he gives them. But the most important thing, the kernel or the OS doesn't know anything about them except that they are one process. So now the kernel knows about a process. Andre has decided, actually, I'm going to take the quantum that the process gives me, the OS gives me for the process, I'm going to split it up between my threads. What's the problem? Without going on to the next page, can anybody see what the problem is? These are very fast, right? Very fast. And they are used, but they're not used as often as these because of one particular reason. What's the problem? Why do we know what the problem is? Any guesses? Okay, so I'll tell you what the problem is, right? So we all agree that a process has a state, yeah? It has a state. It can be ready. Well, it's going to be slow. Yeah. Well, actually, this is going to be slower. This is going to be quicker. So we all agree. The problem is the state. We all agree a process has a state. It can be ready, running, and what's the other one? What's the other one? Waiting. Okay. So say I have up here, I have my little, yeah, that's grand, yeah. I have my little program up here, right, my process up here. So the kernel has fired off the process. I've decided to use a thread library so I can have 3 threads in my process, right? Because I've decided, okay, I have a lot of number crunching going on here, blah, blah, blah. And I've split it into 3 threads. One of those threads has to write to disk. What's going to happen to the other 2 threads? Exactly, right? So essentially, unless if I have any I/O in my design at all, I shouldn't use this user level threads, because if I do, the minute any thread does any I/O, whether it's waiting for a keyboard or writing to a slower disk or whatever, the others, the minute that happens, the OS is going to put my process into a wait state, because that it only knows about the process. It doesn't know anything about this crap, right? The other 2 are going to be in a wait state as well. So it's useless if you're doing I/O, right? Very good if you're not doing I/O, very quick, but there's very little thing at this stage that is purely nothing and never going near a hard disk, right? But it is, you will find things, okay? So that's its big problem. Whereas this one doesn't have this problem. This one essentially are scheduled independently by the OS per thread. So if this thread does slow I/O, these lads still have their own state. They're still running, okay? Well, one of them is running, one of them is, well, they might be on 2 separate cores, right? Okay, whereas this doesn't matter how many cores you have, yeah? This is never going to be able to take advantage of multiple cores if one of those does an I/O. So hopefully you get that. There's a diagram on the next page which is very complicated, but hopefully if you understood what I just told you, you'll get it. So this, oh my God, Pierce, what's this? So on the left hand side of the page, we have user level threads. On the right hand side of the page, we have kernel level threads, okay? So let's take up here for a minute. What is this trying to say? This is trying to say user level threads. Here's an example. I've got 2 processes. The kernel knows about 2 processes. And in these processes, I'm using some sort of thread, user level thread design. And this process has 3. This process has 4. So I think we can understand that so far. Okay. Over here, I have the exact same thing, but I'm using kernel level threads. So I have 3 threads, 4 threads. Now the kernel has a process table, but it also has TCBs. It also has thread table. So it knows about all those threads. It knows they exist. It knows what state they're in, blah, blah, blah. Okay? Now have a look and see what happens when we schedule these. So what does it say down here? Possible scheduling of user level threads with a 50 millisecond quantum. Right? So the OS gives us a 50 millisecond scheduling quantum. And inside that threads, we're going to say are run at 5 milliseconds, right? So there's a little, this library here is going to decide if I get a quantum from the OS, I'm going to schedule my threads at 5 milliseconds. I'm going to give them all 5 milliseconds, right? So essentially what happens is the OS gives us 50 and this library goes, okay, I'm going to give 5 to him, then 5 to him, then 5 to him, then I'm going to go back to him, I'm going to give him 5, then him 5, then him 5. Okay, so I think you probably can get that. So That's what basically happens. So on this side, here we go. These are the threads. What's possible scheduling is A1, A2, A3, then A1, A2, A3. Okay, so do you understand that? The OS gives 50 milliseconds to this guy schedules that 50 milliseconds between these threads. So obviously you can only ever get the A1s because it doesn't know anything about these. You can't have a scheduling of A1, B1, A2, B2. You can't have that, all right? Because the 50 milliseconds got given to him and he can only give it to the A's. Whereas if you come over here, the kernel is responsible for the scheduling of the threads. So the kernel can go A1, then B1, then A2, then B2. All right. So it's a much even spread of what gets scheduled. Okay. So hopefully you can understand that. All right. Hopefully. Kernel level threads. As I say, I'm not sure there's anything here that I haven't explicitly said already, but I'll read through it anyway. Managed by the OS, kernel level threads are. User level threads are not. Everything is implemented in kernel code. Can utilize multiple cores. That's fine. Very good choice for processes that block frequently, because obviously then if a thread blocks, the other threads aren't affected. If one thread blocks, it doesn't cause the entire process to block, whereas user level it does. They're on the next page. They do have disadvantages. They're slower. Okay, fine. They're slower in terms of creating them, in terms of switching them, blah, blah, because you're using the OS. But their advantages, I think, outweigh their disadvantages. A context level switch involves more steps, yeah, because obviously if you're up here, the steps to flick between him and him are very, very small, whereas because the OS has nothing to do with it, whereas to flick between here and here, the OS is involved. And finally, they're not portable because the implementation is operating system dependent. Okay, yeah, that's actually quite important. If you have something in Java or whatever, and you wrote a specific library, it's in your space, right? So it's totally portable. Whereas this is down in the OS land. It's not portable, okay? It's OS specific. Now, having said that, there's lots of pthread is portable, things like that between Unix and Linux and all that sort of jazz. Okay, user level threads. Okay, they're sort of the opposite. They're managed by a user level library, so Andre wrote his own, yeah? And it doesn't mean the kernel knows, it doesn't, yeah. So the only thing the kernel doesn't know anything about the threads. It knows about the process. So all it handles is the execution, right? It basically gives you a quantum, yeah? This is an important point. The lack of cooperation at the user level of the kernel is a known disadvantage. The kernel may not favor a process that has many threads. So let's go back here for a second. So the problem is, if I have a process that has 3 user level threads, and if I have a process that has 20 user level threads, they're both going to get the same quantum. Okay? So in the case of the 3, this will divide it up between the 3. In the case of the 20, it has to divide it up between the 20. So it's not the best solution if you've got some process with a few threads and some process with many threads. It's not, each thread isn't going to get an even slice of CPU time. Whereas in this one, they are. Okay, that's what that point means. It is an important point. And they're fast in comparison. Yeah, that's why they're fast. And good choice for non-blocking tasks. So if you have code and you know it's not talking to slow peripherals and it's not blocking, then they're fine. But if you do, they're not. Okay, so typically this is how they work. I'm not going to read this. This is very, very straightforward. Okay, the important point is the last one. The kernel is unaware of anything that's going on with user level threads, right? It just continues to schedule the process as a unit and assigns a signal execution state, ready, waiting, running to that process. Okay, that's the important point. So user level, this is the big disadvantage. If a user level thread makes a system call that blocks, okay, like whatever, reading a file from an I/O disk, or writing a file, or waiting for a keyboard, yeah, the kernel will move the whole process to scheduling, and the other user level threads, they will have to wait too. Okay, whereas the kernel level threads, this is just in writing what I've already been telling you. All right. So here's a question for you: can user level threads take advantage of multi-cores? After you've listened to me waffle for 50 minutes now, what's the answer? And the answer is no. Okay, so they can't run on 2 cores because the kernel will schedule the process, not the threads. Very, very simple, right? And if the kernel threads were used, they can. That's the problem. Okay, so that's the thread stuff. That's the intro. That's the. It's a tricky one, right? There's a fair bit in it, right? So my advice to you is, what I will do is I'm going to give you a 10-minute break now, and I'm going to kill this video so that this is totally self-contained in a video about threads. And my advice is go back and watch it again and make sure you get it, all right? Because it makes the rest of the stuff we're going to do in the labs over the next few weeks a lot easier if you get it, all right? So I'll kill this video. We'll come back at, let's say 10 past 10. We'll come back at, and we'll do some more stuff. Is that okay? All right, so 10 past 10, I'll resume at 10 past 10. Okay? All right, I'll see you then.